Welcome to the new era of video creation with Bayozi. This is our new series on teaching deep learning. Today we will discuss the recurrent neural networks. Here are the contents. Recurrent neural networks, RNNs, are a class of neural networks designed to process sequential data. Unlike traditional feedforward neural networks, RNNs have loops within their architecture, which allows them to maintain a memory of previous inputs. This characteristic makes them highly suited for tasks involving sequence-based data, such as natural language processing, NLP, speech recognition, time series prediction, and more. While traditional networks assume that inputs are independent of each other, RNNs can capture temporal dependencies by storing information from previous time steps, making them ideal for tasks where the order of inputs matters. Today, RNNs are widely used in many areas such as text generation, machine translation, and predictive analytics. In this lecture, we will explore the architecture, functionality, and applications of RNNs. The architecture of an RNN is relatively simple yet powerful. An RNN consists of three main components: the input layer, the hidden state, and the output layer. At each time step, the network receives an input, such as a word or time series value, and updates the hidden state, which serves as a memory that contains information from previous time steps. The key feature of RNNs is the recurrence. The hidden state from the previous time step is passed along with the new input to the next time step, allowing the network to maintain temporal dependencies across the sequence. The output of the network is typically a function of both the current input and the hidden state. This feedback mechanism enables RNNs to model sequential dependencies, which makes them suitable for tasks like sequence prediction, language modeling, and speech synthesis. At the heart of RNNs is the recurrent connection that passes information from one time step to the next. Mathematically, the hidden state at time step t is updated as a function of the current input xt, the previous hidden state ht1, and the weights of the connections. This can be expressed as ht fwxt t1 by ht fwxt plus t1 plus b, where ww is the weight matrix for the input to hidden connection, yu is the weight matrix for the hidden to hidden connection, bb is the bias term. The function ff typically represents a non-linear activation, such as TNH or real u. This recurrent connection allows RNNs to capture temporal dependencies across time steps, enabling them to remember previous inputs and influence the current state. This is in stark contrast to traditional feed-forward networks, where each input is treated independently, and there is no concept of memory or sequence in the input. Training RNNs follows a similar process to training traditional neural networks, but with an additional challenge due to the recurrent structure. During the forward pass, the network computes the outputs and updates the hidden states across all time steps, passing information through the recurrent connections. However, during the backpropagation step, RNNs require a specialized method known as backpropagation through time, BPTT. This involves unrolling the network across all time steps and then calculating the gradients at each time step. The gradients are then propagated backward through time to adjust the weights. However, this process can lead to two key problems: vanishing gradients and exploding gradients. In the case of vanishing gradients, the gradients become very small as they propagate backward, making it difficult for the network to learn long-term dependencies. Exploding gradients, on the other hand, occur when gradients grow exponentially, leading to instability in the learning process. Proper weight initialization, regularization techniques like gradient clipping, and careful optimization are essential for training stable RNNs. The issue of vanishing gradients arises during the backpropagation step, when the gradients become very small and decay exponentially as they are propagated back through time. This issue makes it difficult for RNNs to learn long-term dependencies, as the network forgets important information from earlier time steps. Conversely, exploding gradients occur when the gradients grow excessively, leading to very large updates and instability during training. Both of these issues can severely impact the performance of RNNs, particularly in tasks requiring long-term dependencies, such as language modeling or time series forecasting. To mitigate these problems, Several techniques are commonly used, such as gradient clipping, where gradients are scaled back if they exceed a certain threshold, ensuring they remain within a manageable range. Other strategies include the use of alternative RNN architectures, such as LSTM or GRU, which are designed to combat the vanishing gradient problem more effectively. One of the most successful solutions to the vanishing gradient problem in RNNs is the long short-term memory, LSTM, network. LSTMs are a type of RNN that introduces specialized gates to control the flow of information within the network, making them more capable of learning long-term dependencies. An LSTM cell consists of 3 key gates. Forget gate decides what information from the previous time step should be discarded. Input gate determines what new information should be added to the memory cell. Output gate decides which information from the memory cell should be output as the hidden state. These gates, in combination with a memory cell, allow LSTMs to retain and update information over longer sequences, which significantly improves their performance on tasks like language modeling and machine translation, where long-term dependencies are crucial. LSTMs are less prone to vanishing gradients due to their internal mechanism for controlling information flow. The gated recurrent unit, GRU, is another type of RNN designed to address the vanishing gradient problem. GRUs are similar to LSTMs but have a simpler architecture. Instead of having 3 gates like LSTMs, GRUs use 2 gates. Update gate determines how much of the previous memory should be retained and how much of the new input should be incorporated. Reset gate controls how much of the past information should be forgotten. Because GRUs have fewer gates and parameters than LSTMs, they are computationally more efficient and often faster to train. While LSTMs tend to perform better on more complex tasks, GRUs have been shown to work equally well in many cases, and they are preferred in scenarios where computational efficiency is important. GRUs are often used for speech recognition, text generation, and other sequence-based tasks where capturing dependencies over time is crucial. A bidirectional RNN, bi-RNN, is an extension of the basic RNN that processes the input sequence in both forward and backward directions. While a standard RNN only processes the sequence in one direction, from past to future, a bi-RNN considers both the past, backward, and the future, forward context, which can be particularly useful in tasks like machine translation and speech recognition, where both preceding and succeeding words contribute to the meaning of a sentence. The forward pass captures information from previous time steps, while the backward pass captures information from future time steps. This bidirectional structure allows the model to be more context-aware and can improve performance on various NLP tasks, including named entity recognition and part-of-speech tagging. RNNs are particularly well-suited for tasks that involve sequential data. In the field of natural language processing, NLP, RNNs are used for a variety of tasks, including text generation, machine translation, and sentiment analysis. RNNs can model the sequence of words in a sentence and generate meaningful predictions based on the context of previous words. In time series forecasting, RNNs are employed to predict future values in a series based on historical data, such as predicting stock prices, weather patterns, or electricity consumption. Additionally, RNNs play a crucial role in speech recognition systems, where they convert spoken language into written text. RNNs are also used for video analysis and activity recognition, where the temporal sequence of frames helps detect actions or events in video data. RNNs have several advantages when working with sequential data, as they are designed to capture temporal dependencies between elements in a sequence. Unlike traditional neural networks, which treat inputs as independent, RNNs can remember information from previous time steps and use it to inform future predictions. However, RNNs also come with limitations. One major issue is the difficulty in training on long sequences due to problems like vanishing and exploding gradients. These problems make it challenging for the model to learn long-term dependencies effectively. To overcome these issues, architectures like LSTMs and GRUs have been developed, which improve performance on long sequences by controlling the flow of information. While these architectures solve some of the issues with traditional RNNs, they still come with computational costs. When designing models, there is a trade-off between achieving high performance and maintaining computational efficiency. When applying RNNs in practice, it's crucial to select the right architecture for your task. If your task involves modeling long-term dependencies, using LSTM or GRU networks is often the best choice, as they are specifically designed to address issues like vanishing gradients. On the other hand, for simpler tasks, a standard RNN might suffice. Hyperparameter tuning plays a significant role in optimizing RNN performance, with parameters like sequence length, how long the input sequence is, batch size, and the number of hidden units needing careful adjustment. Common optimizers like ADAM, RMS-prop, and SGD are used for updating network weights. Another practical approach is to leverage pre-trained models, which can be fine-tuned for specific tasks, especially when you have limited labeled data. In language modeling, RNNs are used to predict the likelihood of the next word in a sentence given the previous words. This task involves capturing long-range dependencies in text, which makes RNNs a natural fit. For example, in text generation, an RNN might be trained to predict what word should come next in a sentence based on the words that have appeared so far. This type of model is used in applications like auto-completion, where the model suggests the next word or phrase based on the user's input. Language models trained with RNNs, especially LSTMs or GRUs, have been fundamental in building systems for speech recognition, text generation, and machine translation. By learning from vast amounts of text data, RNNs can generate human-like text that follows grammatical structure and makes semantic sense. RNNs are highly effective for time series prediction, where the goal is to predict future values based on historical data. For example, in finance, RNNs can be used to predict stock prices by learning from past price movements. In healthcare, time series models can predict patient vitals over time, while in the energy sector, they can forecast electricity demand. RNNs, especially with their ability to capture temporal dependencies, outperform traditional methods like linear regression when dealing with data that has inherent sequential patterns. The ability to process data over time allows RNNs to predict future events with higher accuracy, especially when combined with architectures like LSTMs or GRUs. Speech recognition systems rely on RNNs to convert spoken language into written text. In this domain, RNNs are used to model the sequential nature of speech, where phonemes, the smallest units of sound, are strung together to form words and sentences. RNNs and their more advanced variants like LSTMs can learn the temporal dependencies in speech patterns, allowing them to map input audio features to their corresponding transcription. This ability is essential for applications like virtual assistants, such as Siri or Alexa, and transcription services. RNNs allow these systems to process continuous streams of audio and generate text in real time, significantly improving the user experience. To conclude, recurrent neural networks, RNNs, are powerful tools for processing sequential data, enabling models to capture temporal dependencies in tasks like language modeling, time series prediction, speech recognition, and video analysis. While they have some limitations, such as the vanishing gradient problem, architectures like LSTMs or WAVs and GRUs have made RNNs more effective for longer sequences. In recent years, architectures like transformers have gained prominence, especially in NLP tasks, due to their ability to handle long-range dependencies more efficiently. However, RNNs remain a cornerstone of sequential learning. Understanding their strengths and weaknesses will continue to be crucial as we explore even more advanced architectures for future applications.